Hey, Chem 240 students. This is Dr. Ricardo. I'm going to start with reviewing my notes. These are the same notes that I would have used in the course. I'm going to break them up into kind of 1 hour sections. So it'll probably take us 2 or 3 videos to complete chapter 11, which is on states of matter, focusing on liquids, and then another 2 or 3 lecture videos on solids, and that will constitute all of the lecture material for chapter 11 and 12. We'll have an exam based on chapters 11 and 12 together. That'll be our first exam. So in order to get started, the first thing that we need to spend a little bit of time talking about is the different phases of matter and the transitions between them. So whenever you change matter from one of the 3 traditional states, be it a solid, a liquid, or a gas, that transition is called a phase transition, and those different phase transitions have names. So many times the names of those phase transitions coincide with common sense or what people use in general. So one example of that is the phase transition that takes place when something melts. Okay, so melting under ordinary pressures occurs at a particular temperature. So the melting point for solid ice to make the transition into liquid water happens at 0 degrees Celsius, as long as you're at ordinary pressures of 1 atmosphere of pressure. If you start to adjust the pressure, either by having the system at a higher pressure or a lower pressure, that number can change. So we're not used to that. We're used to thinking about 0 being the melting point for ice under any circumstance. But in reality, you should specify what the pressure is. So at 1 atmosphere of pressure, the transition from a solid to a liquid is called melting, and it's a change of state of a solid to a liquid. Melting sometimes is also called fusion, which kind of is flipped over, right? Because fusion, to me, sounds like you're putting the molecules closer together, when we know melting is actually separating the molecules. So I can't help that confusion. Okay, so the heat of fusion means the amount of energy it takes to melt something. So if we write it out as a chemical reaction, we write H2O solid undergoes a chemical reaction, so we draw an arrow to make H2O liquid, and we can call that process either melting or fusion. Okay, so delta H for fusion, or delta H for melting. Delta H means the change in enthalpy, which is the change in the amount of heat content that the substance has at constant pressure. So the delta H is probably the most important thermodynamic quantity that we're going to study in this course, and you already studied in Chem 1. And delta H is a positive number for this particular process, meaning that if you want to melt ice, you need to add energy to the ice to break the bonds between the water molecules in the solid phase and separate them into water molecules in the liquid phase, where they have a lot more energy and they're moving around. So the sign of it, I can tell you the exact number, but the sign of it is more important at this point. The sign of it is a positive number. If you went in the reverse direction and you froze liquid water and made ice, that would have a delta H for freezing that would be equal in magnitude but opposite in sign. So that number would be a negative 140 instead of a positive 140. So if you remember back from Chem 1, whenever something has a positive delta H, we call that endothermic. And again, what is delta H? You can think of H loosely as heat, where delta means the change in heat, energy when the reaction is done at constant pressure. We call that the change in enthalpy. Enthalpy is the change in heat done at constant pressure. And we're going to try, for the most part, all of the chemical reactions we're going to do at constant pressure. So that's why delta H will be our most important thermodynamic term. Again, positive is going to be called endothermic, to put energy in. Negative is going to be exothermic, to release energy. Okay? So two numbers going to be equal in value, opposite in sign. How much energy does it take to freeze something? How much is released is going to be the same number, only with a negative sign, as how much energy is released when it melts. Okay, so melting is positive, freezing is going to be negative. And the technical word for the negative value is going to be exothermic. So that's what freezing is going to be, and we'll talk about that down here. So melting is this direction. Let's talk about freezing. Again, equal in magnitude, opposite in sign. The change of a liquid into a solid. Here's the chemical reaction. Water liquid goes to water solid. That process is called freezing. Delta H for freezing is going to have a negative value, and that's exothermic, downhill to give off energy. This one is uphill to store energy in the bonds. Okay? Just like I mentioned before, delta H for freezing is equal to negative delta H for fusion. Remember, fusion is the fancy word for melting. Freezing was just going to be called freezing. Equal in magnitude, opposite in sign. Okay? So for the same substance, under the same conditions. Okay, so we'll just use water as an example, but each substance, right, if you had dry ice, which is solid carbon dioxide, you could melt it to make liquid carbon dioxide, and it would have a delta H that is different than the value for water. But one thing that would be for sure is to make the transition from liquid carbon dioxide to solid carbon dioxide would be equal in magnitude and opposite in sign from the reverse process for carbon dioxide. Okay, so these are always for the same substance under the same conditions. Okay, so second page of the notes. All right, the next transition, besides transitioning between the solid and the liquid phase, is transitioning between the liquid phase and the gas phase. Okay, so going uphill, right, and putting energy into the system to go from the liquid to the gas phase is called vaporization. We shouldn't call it boiling, because boiling is a special situation of vaporization. So the general term for this reaction right here of something going from the liquid state to the gas state is called vaporization. Okay, so vaporization has a number attached to it. How much energy does it take per gram or per mole of the liquid water? You could look up that value. Delta H for vaporization is going to be a positive number. It's going to be an endothermic process. So uphill, because you're going to put energy into the water molecules to break all those strong forces of attraction between the water molecules to separate them into the gas phase. In fact, this number, delta H of vaporization, is much, much higher than this number back here. I'm going to grab the numbers in a little bit so that you can see them, because this one is uphill to melt something. This one is also uphill to vaporize something, but this is going to probably be close to 10 times the amount of energy to do this process per gram. Okay, so delta H of vaporization is an endothermic process because it has a positive value. You have to put energy in. What's the opposite of vaporization? That's called condensation, going from the gas phase and settling out into the liquid phase. Let me just finish my 2 over here. Okay, that's called condensation. Delta H of condensation is a negative value. It's a downhill process. When things condense, they release energy. That would be exothermic. These two guys, just like on the last page, would be equal in magnitude, opposite in sign. Here they are. Delta H of condensation equals negative delta H of vaporization. Okay, I'm going to grab those for you in a second, right after we finish this section, so you can look at what the numbers are. Okay, sublimation is the process when you go directly from a solid to the vapor phase. Okay, so this is something that you think of typically with dry ice. When you see the smoke coming off of dry ice, under that particular pressure and temperature, if you have dry ice out in the open on a 70-degree day, it's going to skip the liquid phase. And under those conditions, there's nothing special about it. Many substances do this. In fact, under the right conditions, you can even get water to do this, to go directly from the solid to the gas phase. That's called delta H of sublimation. It requires energy. Okay, if you have a piece of dry ice, where is it taking the energy from? It's sucking the energy out of the air. So the air around it is going to become cooler while this change of phase occurs. So that would be, for water, it would be H2O solid goes to H2O gas. Okay, it is a uphill process, so it's going to have a positive delta H of sublimation. And other interesting thing about the thermodynamics of this is delta H of sublimation is equal to delta H of fusion plus delta H of vaporization. So if you know how much energy it takes to go and do this in 2 steps, you can just add them together and see how much energy it would take to do it directly. It makes no difference which way you go. If you go and stop off at the liquid and then go to the gas, or if you go directly, it requires the same amount of energy. There's a graphics on the next page that'll show this. Okay, and again, here's the process. We're just using water as an example. Any substance can undergo these transitions. Sublimation is going from a solid to a gas. Okay, the opposite of sublimation is called deposition, right? You can think about it as creating frost, okay? Happens all the time. In the wintertime on your car, you go out in the morning and you see this white powder on your windshield of your car, but yet it never snowed at night. So where did this stuff come from? Well, that was the water vapor in the air settling out and going directly to frost on the surface of your car. Okay, snow is also a form of going directly, right? Snow is very different than frozen rain, right? Frozen rain is sort of boring. Snow is when to create the snow particles, you go directly from the gas phase. Things cool down in the upper atmosphere, and it settles out onto into snowflakes. Okay, so just like with the other 2 processes, deposition is negative. It's the opposite of sublimation, right? In this case, you would be settling out and releasing heat, so it's going to be an exothermic process. Delta H for deposition is equal to minus delta H of sublimation. Okay, so this next graphic down at the bottom of page 4 of your notes kind of sums up everything that we just talked about. Okay, what is the axis on the left? Well, this is H, which is the total enthalpy of the system. Okay, so this is the enthalpy, right? So if you go from one place to another place, the change in H is called delta H. Okay, so all of these different arrows here are delta H's. Okay, and so just like we talked about before, there's going to be 6 of them. Okay, so if you go straight from a solid to a liquid, that's delta H of fusion. Uphill requires energy, endothermic positive. The opposite process is here, freezing, right? Come up here, go from a liquid to a vapor. Endothermic requires energy. Delta H of vaporization would be positive. It would be equal and opposite to the opposite process, delta H of condensation. So the length of this arrow is the amount. The direction is the sign. So up is positive, down is negative. So this one is going to be a positive sum value. This one will be negative sum value. Okay? This one's going to be positive that value. This one's going to be negative that value. Now, cool thing about enthalpy is said to be a state function. So it's independent of the pathway that you take, right? All that matters is that you start over here and you end up over here. So if that's the case, then stopping and taking a break at a liquid, right, and then eventually going to the vapor should be the same as going straight. And that's true. Delta H of sublimation is going to be this positive number. Let's make it 150, right? Then this, if this one was 100 and this one was 50, 100 plus 50 would equal 150. You have to get the same amount when you add this line and this line up as if you went directly. Let's try it in the opposite direction. Going straight from a gas to a solid is called deposition. You come downhill, it's going to be negative that same number, negative 150. This one would have to be negative 50, and this one have to be negative 100. They would have to add up, okay? So this is not drawn to scale. It's just supposed to show you all of the different possible processes, okay? And again, another thing we're learning here is H is said to be a state function. It's independent of the path. Doesn't matter how you get from one place to another. All that matters is what's the starting point and what's the highest point. An analogy to that, to this idea of a state function, would be the altitude of a mountain, right? If it's a 5,000 foot mountain, and you're starting at the base of the mountain, right? Most bases of the mountains isn't 0 feet because you kind of have to drive up into New Hampshire or Maine or wherever you're going hiking. So let's say at the bottom of the mountain is 1,000 feet. Well, if there's two different trails that take you to the top, and one is very, very steep, and you get there and you only have to walk 3 total miles to get to the top of the mountain, okay? And another one takes its time and is a gentle one and takes 10 miles to get to the top. Well, one is longer than the other, but they both have the same exact change in altitude because you start at the same base camp. One takes a meandering path to make it to the top of the mountain. One goes straight up. But the change in the height would be the same, right? 5,000 feet minus 1,000 feet would be 4,000 feet. That's all that matters. So H, like many properties in chemistry, is a state function, independent of the path in which you take to get from one place to another. Okay? And so are all the delta H's. All of these phases are said to be in a dynamic equilibrium. It's not that nothing is happening, okay? It's that all of the things are happening at the same time. In fact, there's a very special point for substances called the triple point. And a triple point is a place when the solid, the liquid, and the gas can all coexist. Water has a triple point. Its triple point is pretty close to 0. It's just at a slightly reduced pressure. And at that reduced pressure, you can have ice, water vapor, and liquid water all coexisting, okay? All coexisting. And you came back, if you stayed exactly at that temperature, you came back 2 hours later, you would have the same proportion of solid, liquid, and gas. Right? Some of the molecules might have changed. Some of the ones who used to be a solid are now up at the gas, and some of the ones that are liquid used to be in the gas. But the net amount of each would stay the same. So it would seem to you like nothing happened, when really what it is that 3 things are happening. These 3 processes are happening, but they're all happening at an equivalent rate. So the amounts of each substance would be the same. That's what happens a lot in chemistry. Looks like nothing's going on, but really a lot is going on behind the scenes, but the net change is 0. That's called the dynamic equilibrium. Okay? All right, so here's some of those values that we were talking about. Whenever a change of state involves going to a less ordered state, energy must be supplied to overcome the intermolecular forces, and we talked about this. So these are the uphill processes. Things are endothermic whenever delta H is positive. So going from a solid to a gas, okay, that's sublimation. Going from a solid to a liquid, that's fusion. And going from a liquid to a gas, that's vaporization. All of those would have positive numbers, okay? And the exothermic processes, the ones that are negative, are the reverse ones. Look, these ones here, these 3 are just the reverse of those 3 here. Going from a gas to a solid, going from a gas to a liquid, or going from a liquid to a solid, all would release energy and heat up the room. These would require energy to occur. These would release energy. Okay, here's the numbers for water. Delta H of fusion, the enthalpy change associated with melting a solid is 6.01 kilojoules per mole. Okay? If you divide this number by 18, the 6,010, right? That's basically what that is, joules. And you divide it by 18, which is the molecular mass or the molar mass of water, right? Water it has 1 oxygen and 2 hydrogens to give it a molecular weight of 18. So if you divide this in kilojoules per mole, you would get this number in kilojoules per gram. Okay? So either one you can work with. Most of the time for us, In this chapter, we're probably going to be more helpful to do it in kilojoules per gram. So for each gram, this is how much energy it takes to melt it. So if you want to melt 10 grams of ice to make liquid water at 0 degrees, it's going to be 10 times this number, because this 334 is per gram. This number is per mole. Okay? All right, notice if this guy is 6.01 kilojoules per mole, right? That's this process here, solid to a liquid. Then a liquid to a solid would be negative 6.01 kilojoules per mole, right? Equal in magnitude, opposite in sign. Okay? What is the other important one that we would, now you don't have to memorize these, you'll always get these to work with on a test. How much energy does it take to vaporize 1 mole of water or 1 gram of water? That's called the enthalpy change associated with the vaporization of a liquid. Delta H of vaporization is 40.67. So look, this number is only 6, and this is 40, right? So that's a lot higher, right? So let's just see, 40, I'll put the digits in too, 40.67 divided by 6.01, okay? It's 6.76, so almost 7 times as much energy is needed to vaporize a gram of liquid water as compared to melting 1 gram of solid ice. So this is a lot tougher process, 7 times harder to melt something than it, to boil something or vaporize something than it is to freeze it, than it is to melt it. So again, where does this 2,259 come from? If you take this number, right, and you change it from kilojoules to joules, that means multiply it by 1,000, you'd get 40,670. Take that number divided by 18, and you'll get how many joules per gram it is for water, right? So from here to here is divided by the molar mass of water. From here to here is divided by the molar mass of water. Okay, just put those two numbers together. If you take the 40.67 and you add on to it the 6.01, right? Add those two numbers up, these two, you'll get 46.86. That's delta H of sublimation. Remember, delta H of sublimation is the same to go straight from the solid to the gas as it would be to do it in steps. So those two have to add up together. And again, I just divided it by 18 if you need it in grams. Okay? So nothing unique here. Looks like 6 different numbers, but I just gave you 2 of them, and you can make 6 out of them, right? You can make 2 of them by flipping them around. You can make the third one by adding them up, and then after you add that one up, you can get the other one by flipping it around, right? Because this 46.86 kilojoules per mole is how much energy it takes to do this process, go from a solid to a gas, right? So how much energy does it take to go from a gas to a solid? It would release that much energy. Same number, 46.68, only with a negative sign on it. Okay? Again, don't have to memorize any of those. Okay, next thing hopefully is a review from Chem 1 is what happens when you are not changing the phase. You're just in the middle of a particular, you're at a temperature where you're in one phase of the particular substance and you want to add heat to it. Well, that you need the specific heat formula, right? So if you're at a phase change point, what happens is all the energy goes into changing the phase of the solid to a liquid or the liquid to a gas. So that would happen for water at 0 degrees and 100 degrees Celsius, right? Those are the 2 normal phase change temperatures. But what happens if you're at 35 degrees and you have liquid water? 35 degrees Celsius, well, you're pretty far away from 0 and you're also far away from 100. So if you start adding energy with a hot plate or a Bunsen burner, how is that energy absorbed by the liquid? And how can you map out how fast the temperature will change or what the eventual temperature will be? Well, to do that, you need this formula, right? You need the specific heat formula. So the specific heat of a substance, capital SH, is the energy required to raise the temperature of 1 gram of a sample of matter by 1 degree C. And remember, 1 degree C is the same thing as 1 Kelvin, because the size of the Celsius degree is identical to the size of the Kelvin degree. Okay? They start at different points. One starts at 0, the other one starts at 273, but when you go up 1 degree Celsius, you always go up 1 degree Kelvin. So notice, delta H is not for phase change now. This is just the heat of changing the temperature of the substance. There's 3 factors that go in. The bigger the substance, the more mass it is, the harder it is going to be to change the temperature. Therefore, that's going to affect delta H, right? And that's to the first power. Whatever the amount of temperature that you want to change is going to be important. If you only want to go up 1 degree versus 10 degrees, well, obviously 10 degrees, you're going to plug in a 10 here versus a 1, right? And 10 degrees is going to require 10 times as much energy as 1 degree. So that makes sense, right? So those 2 things. And the third thing is each material has an intrinsic value called its specific heat. The harder it is to heat something up, the bigger this number is. Water is very, very hard to heat up. It takes a lot of energy to heat it up. So water has a specific heat that's on the high side compared to other substances. Most other substances are less than water. And I'll tell you what water's value is. Water's value is exactly 1 calorie of heat energy for each gram for each degree C. So that's where the word calorie comes from. It's specifically defined as the specific heat of water. Okay, so this is the formula you're going to use when you're not dealing with a phase change, right? And you want to know how much energy it takes to heat something up or to cool, how much energy is released when something gets cooled off. Okay, so let's talk about signs for a second. Delta T, the change in temperature, which is T2 minus T1, right? You're familiar with that concept, delta anything, right? Delta T, take the final temperature minus the initial temperature. Not just the bigger one minus the smaller one, the last one minus the first one. The order does matter, very much so, okay? So delta T can be positive or negative depending on if the temperature has gone up, has changed upward, or changed downward. So this guy can be positive or negative. These 2 are strictly positive. These are going to be the mass in grams. There's no such thing as negative mass in our world, right? We're not doing antimatter or anything fancy like that. And the specific heat is also always going to be positive. Think about it. It has to be. All specific heat values have to be positive because it's the amount of energy it takes to raise the temperature of something. So if you're raising the temperature, you have to put heat in. Otherwise, you could have this material, if it had a negative specific heat, you would be heating it up and it would be getting colder, right? That's impossible. If we had a material like that, we'd all be rich. Our air conditioning would be a lot cheaper. The way we run our air conditioning is a fancy, smart, man-made way of kind of removing heat from our house by putting a couple of processes together. It's not easy to cool things off in a straight way. So we've kind of rigged this really cool system up called air conditioning, and I'll explain it to you at some point. Okay, so here's our 2 formulas. If there is a temperature change and no phase change, okay, so you're in the middle of the system, somebody asks you a question about, hey, I've got 30 grams of water at 15 degrees Celsius. So that's definitely liquid water, right? So if you're at 1 atmosphere of pressure, you're talking about liquid water. Well, if I want to raise that temperature and add heat to it, this is the formula I'm going to use, right? I'm going to use the delta H is the specific heat times the mass of the sample of water times how much the temperature's changed, okay? Or these 2 things never collide. You never have to worry about the same thing. It's one or the other. Or if you're at one of these special phase change temperatures, okay, at those points, all of the energy goes into changing the phase and the temperature does not change. So delta T is going to be 0. So if you tried to use this formula up here, you're always going to get 0, right? Because there's no temperature change. So what am I talking about? Someone asked the question, hey, I've got 40 grams of ice and I want to melt it to liquid water. Well, the ice is at 0 and the water, when you're done, is going to be at 0. So how much energy does that take? All you need are 2 factors. you need to look up delta H for the phase change per gram and multiply it by the number of grams. Or if somebody gave you delta H, the bar just means per unit. So it could be per gram or per mole. Or if somebody gave you delta H for the phase change per mole, you just multiply by the number of moles. So for us, we're probably going to do them both. To be consistent, we'll do them this way. They'll both use the mass. Okay, and I have a sample example at the end of the chapter that you can look at. So here, actually, here's one right now. Okay, there's another one, I guess, at the end of the chapter. All right, so I'm going to read the question, and I'm going to just outline what we're going to do, and then hopefully you take a break, shut the video off, do the math yourself, come back and see if you agree with me. Okay, so here's the sample question. Calculate the enthalpy change associated with converting 1 mole of ice at negative 25.0 degrees Celsius to water vapor at 125 degrees Celsius. So we're starting with ice that's super cool, much colder than we ordinarily see it. We're used to ice sitting in our glass at 0, but you can put it in a freezer, and if that freezer is a deep freeze, you can lower the temperature all the way down to negative 25. So that's the first part of it that you have to realize is ice isn't just always at 0. You can cool the ice below 0. And same thing with water vapor. Water vapor you create it at 100, but we can superheat the water vapor. After it's vaporized, we can continue to heat it and get it from 100 all the way up to 125. So there's going to be a bunch of steps in here, and let's take a look at what they're going to be. Okay? So first thing that you could probably do is draw a little chart like this for yourself. Okay? And then you realize that since enthalpy is a state function, if I can calculate how much energy it takes for each of these 5 steps, all I have to do is add them together, and that'll give me the amount of energy for the whole process. Now remember, the question is so short. How much energy to go from negative 25 degrees for pure water to positive 125? So I'm starting here. Got temperature on the left-hand side, and over here, this is amount of heat added and amount of time. Okay, so as long as I'm moving this way, I'm going to have to add heat to the system. Right? So the total amount is going to be the sum of the part A plus part B plus part C plus part D plus part E. Okay, let's talk about the parts. The first part is I need to get the ice from negative 25 up to its phase change temperature, right, which is 0 degrees Celsius. Now all of this is happening at 1 atmosphere of pressure, so I'll put that over here, 1 atm of pressure. Okay, this way we can easily do the question, and we're familiar with these normal phase change transitions. So I'll always give you these at 1 atmosphere of pressure. Okay, all right, so first thing, I need to heat up the ice, okay? All right, well that's going to, you see that has a slope, that's not a flat part. The temperature is changing while you're heating it up. That's going to involve the specific heat of ice, so we're going to have to look that up. The second one is a phase change. So we're going to not need a temperature difference here. Right here we have a temperature difference. This starts at negative 25 and goes up to 0. Here, the whole thing is at 0. See how it's flat? So all we're going to need is the mass of the ice, which was 1 mole, right? So 1 mole is 18 grams, times delta H of fusion. That was the amount to do the melting. Then we have liquid water from 0 degrees up to 100 degrees. So we need the specific heat of water, the amount of temperature difference, which is exactly 100 degrees here. This one is 25 degrees, right? You finish at 0, you start at negative 25, 0 minus a minus 25 gives you a positive 25 because you went uphill 25, right? Delta T here is positive 25, delta T here is 0, delta T here is 100. Water will stay liquid water all the way from the melting point all the way up to the boiling point. Then I need, this is the hardest one, I need to vaporize the water. I need to boil that water away. So I need to look up delta H of vaporization and multiply it by the amount of matter, which is 18 grams. Okay? And then the last thing, I need the specific heat of steam. Right? I look up the specific heat of steam. I need to go from 100 to 125. So that's a difference of 25. So it's 25 degrees multiplied by the specific heat of steam times the amount of steam in grams. Okay? So I'm going to tell you right now, take a break, see if you can calculate each of these. Right? So we've got two phase changes. This is the fusion, the first one, and this is the vaporization. They're in joules per gram. This is the specific heats. The first one you need is for ice, then for water, then for steam. Now the reason why we're not using 1 calorie is we're doing them all in joules. And it turns out that we said that the specific heat of water was 1 calorie. 1 calorie is exactly 4.18 joules. So we're going to do this problem in joules so that we can be consistent. So use these 3 numbers and these 2 numbers. So if you got 5 numbers, you need them for these 5 parts. So figure out which one it is. And 1 mole, we know, is exactly 18 grams, right? Just from the molecular weight of water. That's right from Chem 1. Okay, so here's the overall process. I have 1 mole of ice at negative 25 degrees. So there's the ice cubes, very cold. Delta H total, I'm going to wind up in the end with 1 mole of steam at positive 125. There's our 5 sections. Stop your video right there. I'm going to put it on pause. Okay, how'd you guys do? I'm going to show you the total answer to take ice at negative 25 and bring it up to ice at 125, and then we'll go through the steps. So the total answer that you should have gotten is either 55.96 kilojoules for that process, right? Or if you did it in joules, right, and you didn't switch to kilojoules, you should have got 55,960, or very close to that. You don't have to get exactly the correct answer, right, because there's always going to be some rounding error. So if you got 56,000 kilojoules or 56 kilojoules or 56,000 joules, you're right on target. And again, every one of these steps was uphill. They're all positive. So the final answer is going to be positive, and it's an endothermic process. So let's take a look at the individual steps. So for step A is not a phase change. It is changing the temperature of water at negative 25 to 0. So we use the specific heat formula. We look up how much energy it takes to raise the temperature of ice. That's 2.09. I gave you that. Multiplied by the mass, right? 1 mole is 18 grams. Multiplied by the change in temperature, 0 minus a minus 25 equals a positive 25. So 2.09 times 18 times 25 gives you 940 joules. Okay? If you want to switch it to kilojoules now, you can. And just that one, just divide by 1,000 and that'll give you 0.94, but you don't have to. All right, now you're at step B, so I'll go back to the map, right? We just did this one, that was step A. Step B is a phase change, so when you have a phase change, you leave out the temperature, and you just need the mass multiplied by the heat of that phase change. So melting is called fusion, so I need to look up the heat of fusion. That was our 334 joules per gram, multiplied by 18 grams. Grams cancel, and I get just joules. So that step was a lot more energy intensive. Changing the phase requires more energy than just changing the temperature. So this was 900 joules. This is 6,012 joules, or 6.01 kilojoules. Okay, now we have water. We're at step C. Step C is not a phase change, so I need the specific heat of liquid water multiplied by the change in temperature, multiplied by the mass. That's right here. 4.18 was given to you. That's in joules per gram degree C. All specific heats are in joules per gram degree C. The phase change numbers are just joules per gram. Multiply by our 18, which is the mass, multiply by the change in temperature, which is positive. The final temperature is 100, the initial is 0, 100 minus 0 is 100. So this times 100 gives you 7,520 joules, or 7.52 kilojoules. Okay, D, I've got water at 100. I've got to go to steam at 100. This is going to be the most energy intensive of all of them. Part D is right over here. This big one, right? I made it long to show it in proportion, that it would take a longer amount of time because more heat is needed. It's hard to boil water. Okay, ever make pasta? It takes a long time to boil the water. Okay, and if you waited to boil the water away, all to go from a big, 18 grams of water until it was all gone, it would take a long time. It would take a lot of energy to do that. Okay, so that one we are right here, right? So I need 2,259 joules per gram. That's delta H of vaporization, which was given to you a couple pages back, right? Here, 2,259 joules per gram times 18 gives you 40,662 joules, or 40.66 kilojoules. Last step, they didn't say stop when the water was boiled away and all in the gas phase. We now want to heat up that steam in the gas phase from 100 to 125. It's the hardest of the three to heat up. Steam is easier, and so is ice. Interesting, right? So per gram, per each degree that you're going to go up, water is about twice as hard as the other two. Okay? We'll talk about that in the next part of the chapter as to why that is, what forces are doing that. Okay, so that one down here, we need 1.84 joules per gram degree C times my 18 grams times 120 minus 100 gives you 25. So this would be 25 times 18 times 1.84. Where'd it go? 1.84. Make this point better. And that gives you 830 joules, or 0.83 kilojoules. So I chose to add them all up in kilojoules because this number was so big, this one over here. But you could have added them all up in joules and that would have been fine. Add them all up, that's how you get the 5596. Again, if you did this and you got 56 or 55.82, anything close, it's important. But it got to be positive though. Good. Okay. All right, so that's a good practice question in calculating the amount of energy that's required for phase changes. Okay, so now we're going to skip to another concept, and that is the idea of vapor pressure, which is related to the process of boiling and also related to the process of surface evaporation. Okay, so these numbers for the amount of energy it takes to vaporize is going to factor into this discussion. So let's give a definition to what the vapor pressure of something is. And you see this in your life all the time. Things are evaporating around us all the time, and sometimes we can feel the pressure of them. And I'll give you a couple of examples. So vapor pressure is the vapor pressure of a liquid. The vapor pressure of a liquid is the pressure exerted by its vapor when the liquid is in equilibrium with the vapor. Okay, so let's say I have some chicken soup here, right? And the chicken soup is very, very warm, and the water molecules are the easiest thing to evaporate off of the surface, so they're kind of coming out of the solution. And it's usually the ones that are close to the surface that are heading in the right direction, that they actually force their way out of the liquid and up into the gas phase. So this is considered an open system. We don't have a cover on it. Okay? In a closed system, or if you take some saran wrap on your chicken soup and put it on the top, what you might notice is if the chicken soup was originally hot, you come back and it's a little bit puffy because creates a physical pressure that pushes out on the surface of the plastic and creates a little bubbling effect. Then come back a few hours later and it cools down and the vapor pressure drops back down, and you'll see it's kind of shrunken in or sunken in. It's the opposite way when you have your cold chicken soup sitting out or in the refrigerator. That's because you had a closed system here, and when the temperature was higher, the amount of water molecules that are in the vapor phase is going to be higher when the temperature is higher. So in a closed system, you build up this pressure here. It can't constantly evaporate and just you lose the material. It gets stuck in this area here in the vapor phase, and in a sense, it gets saturated, right? It gets to 100% humidity. This happens to us in regular life, right? When the air pressure can be developed at a certain temperature in this space here. Okay, so it's the pressure above the liquid, and to really measure it, you need a closed system. You need to somehow make a seal on the top, and you measure what is that pressure, not just the air part of it, but the extra pressure from the evaporating liquid. Gasoline does this, creates a strong vapor pressure. Anything that's volatile would do this. Alcohol has a high vapor pressure. Okay, so this is a dynamic equilibrium because look, I've got arrows. This guy is a molecule of water that's crashing back down into the liquid. This one is going up, this one is going down, this one is going up. So two of them are going up and two of them are going down, so it's a tie. In the closed system, once this air up here becomes saturated, you create a situation where the amount of evaporation is equal to the amount of condensation. So you come back a little bit later, and the same amount of liquid here is the evaporation is going to blow away the condensation because there's nothing to stop these guys from, once they evaporated, just leaving the room altogether. Okay, so that's very important, right? If you want to, let's say you're going to have a wet basement, right? You need to open the windows so that as the water evaporates, the air doesn't get saturated with water vapor and more water can escape, right? So you open all the windows when something is wet, or you have a wet basement or a wet car, right? And let it get hot in there with the windows open. If you let it get hot with the windows closed, you're not doing any good, because all that's going to happen is it's going to go into the gas phase, and then it's going to get cool at night and they're going to go condense again, right? You need to let them out. Right? You can't have standing water around in your basement. You got to get rid of the water because the water will just re-evaporate. Okay, so that's the idea of a dynamic equilibrium. The number of molecules returning to the liquid exactly equals the number escaping from it. Okay, let's take a look at this graph. This is kind of cool. This is the rate of evaporation in a system that initially is open, right? And then we put the cover on it. Okay, so let's talk about the moment we start the experiment, right? If this is time on the x-axis, is when we put the cover on it. So in the beginning, right, the rate of evaporation stays constant all the way through the whole experiment, right? Because there's plenty of water here. There's no limit of water, and they can just keep on evaporating. But what catches up is the rate of condensation. In the beginning, the rate of condensation is 0 because there aren't any molecules. How can they condense? Once I start to build them up, the likelihood of them, remember, they're moving, they're free, right? This is a gas phase up here. They have the most freedom. They're zipping around. They can come crashing. Instead of going up at this initial high rate and going straight, it slows down because it gets saturated. It gets saturated as this fills up with water molecules to the point where it holds as many as it can. At that point, condensation will level off at the rate of evaporation. When the two are equal to each other, that's when the system is at equilibrium. When you've created the system where the rate of evaporation equals the rate of condensation. At that point, you can measure the vapor pressure, put a pressure meter in here, and measure how much pressure you would see in there. And what would you see? The pressure that you would see in here would be the atmospheric pressure on the outside plus a little bit more based on the amount of evaporation. Now remember, if there's air around too, it's going to have a certain amount of pressure, and then on top of it will be the pressure from these added molecules of liquid. So the pressure inside here is slightly higher than the pressure on the outside because it includes evaporation of the liquid. Okay? So this is an important concept, this idea of a dynamic equilibrium. One rate is constant, the other one is zero, but the zero rate is tied with the amount of condensation. Evaporation down, condensation up. Okay. Well, the last thing I want to talk about today is an equation that you can use to measure the vapor pressure of a substance versus temperature. Okay, so let me see if I find one graph that I would like to show better than this. But you know what, maybe what I'll do is just draw it. Okay, if you were to draw, right, the most logical thing that you would be interested in is follow the vapor pressure, I'll call it P vape, of a liquid, right, versus temperature. Okay, and we know this is going to go up because what's going to happen is the molecules inside the liquid are going to have more energy, they're going to have more kinetic energy, they're going to be moving faster, they're going to have the likelihood of them being able to escape the liquid and go into the vapor phase is going to be higher. But like a lot of things in life, it's not going to be linear. Okay? In fact, it's going to be exponential. As you heat them up and give them more energy, the likelihood is going to start to grow exponentially like this. So this is very typical. This might be the vapor pressure graph, what happens to water. And right here, this might be 1 atmosphere of total pressure. So when the vapor pressure of water lower temperatures or higher temperatures, but at this special point, not only do you have surface evaporation, but bubbles can form inside the liquid, and that's what we consider boiling. So that's a special point on the graph, is the boiling point. Okay? And the normal boiling point is the temperature at which something boils at 1 atmosphere of pressure. What's so special about 1 atmosphere? Well, the only thing special about it is it's the pressure we happen to live in on Earth. So we're so used to it, and our total pressure from the nitrogen, oxygen, carbon dioxide, and water vapor, and the other elements, you all add up to a total of 1 atmosphere. So we're used to living at that. Well, this is nice, but hard to evaluate mathematically. So one of the things you do when you get an exponential graph is you say, let me take the log on one side, so I can take ln of p vape on one side, and reverse this. And you've seen this before, right? Whenever you have an exponential, if you do both of those things at the same time and take this not O over T, but 1 over T in Kelvin, that's the way to straighten this graph out. And that's what you're going to see here. So this second graph of the log of the vapor pressure versus 1 over T is going to give you, you're going to evaluate through an equation called the Clausius-Clapeyron equation. So we're going to do the natural log of the pressure, and that's the vapor pressure above the liquid, versus 1 over T. Okay? For water, it's going to turn out to be lower on the graph and have a steeper slope. Now the slope is always going to be negative. These things are always going to be log of that. So let me see if I have some whiteout. I'll make that right now so we don't forget. Okay, we don't need the 2.3 because look, I whited, I don't know if that's a word, right? I whited that guy out and changed it to ln. When I first did these notes, everybody was using a calculator and having to do log. But all you guys have natural log now, so it's much easier. Okay, so let's leave that like that, right? And so that slope is going to be negative delta H vaporization over R. Okay, I'll tell you which R to use. It's the energy R. I think I probably have it down here someplace. It's 8.31 joules per mole Kelvin. Okay, now notice anytime you have a straight line, you can make a graph of a straight line. So y is equal to mx plus b. There's not really anything special about the slope here. Okay, so, but what you can say is ln of p is y, right? And 1 over t is x, and the slope I told you was minus delta H vaporization over R. So here I already got rid of the 2.3. Okay, so that's kind of cool, right? That you will always get a straight line so that if you drew these graphs, you could predict what the vapor pressure is as a function of the Kelvin temperature, right? They're inversely proportional. The log of the vapor pressure is inversely proportional to the Kelvin temperature. Now, since this B is meaningless, what we're going to do is that formula. I didn't do the derivation. I think I did the derivation later on, and you can look it up yourself, but you could pretty much easily see how you get from here to here, right? Because what you want to do is take 2 points. So you would have an ln of P1 and ln of P2. ln of P1 would go with T1, ln of P2 would go with T2. When you subtracted them, right, you subtract to get delta T, you subtract P2 from P1, the B's will cancel out because one will have a B and the other one will have minus a B. So the B's will cancel out. Then you factor out the negative delta H of vaporization over here, okay? And then ln of P2 minus ln of P1, the rules of logs are that you can consolidate that into ln of P2 over P1. So it's probably not a bad idea to have parentheses here. Okay. And then the last thing you do to get rid of this negative sign is you switch these. Look at that. Right? Usually we would do T2 minus T1 when we talked about delta T. But here, we get rid of the negative sign here, right? Or factor out the negative sign, and this becomes 1 over T1 minus 1 over T2. Now, you will have the formula to use on the test. And then last thing you need is you need the R value. It's 8.31 joules per mole degrees Kelvin. Okay, so let me see if I did a to predict the vapor pressure of a liquid at a new temperature if you know the vapor pressure at a different temperature. Okay, so if you know 3 out of these 4 numbers, 2 T's and a P, you can get the last P, or 2 P's and a T, you can get the last T. But most of the time, we're going to have 2 T's and a P. You also need delta H of vaporization. Last thing you could do is you could do an experiment where you had and measured the vapor pressure at 2 different temperatures, and you could calculate delta H of vaporization. So that's something you could solve for. So there are 5 total variables you could solve for: P1, P2, T1, T2, and delta H of vaporization. But honestly, most of the time you're going to be solving for either P2 or delta H of vaporization. Okay. All right. So before we go on to the next page of the notes, let me grab the practice question that I had for this guy. calculate the vapor pressure of N, there's an A under here, an unknown liquid at 25 degrees if the normal boiling point of the liquid is 61.7 degrees Celsius and the delta H of vaporization is 30.4 kilojoules per mole. Okay, so first thing we have to realize is what do they mean by the normal boiling point? The normal boiling point of something is the boiling point under normal atmospheric conditions, which is 1 atmosphere of pressure or 760 torrs. So let's go ahead and do it in torr, right? So torr are equal to millimeters of mercury, are equal to, these things are all the same. I'll just write them down so you remember from Chem 1. 1 atmosphere of pressure turns out to be 760 millimeters of mercury, which are also 760 torr. Okay, so we're going to do it in torr. Okay, all right. So the normal boiling point, right? We don't know what the liquid is, but it's a pure liquid, and it boils at 61.7 degrees. We need to change that to Kelvin. You can't do the Clausius-Clapeyron equation in Celsius or Fahrenheit. You got to get to Kelvin. The translation to Kelvin is just add 273. So let's make that guy our T1. So when we initially know the boiling point, that we have the T1 now, and we have the P1. What's T2? Well, they want to know what temperature, what would the vapor pressure be at 25 degrees Celsius, which is a typical experimental temperature, right? And 25 degrees Celsius translated to Kelvin is 298. You have to just add 273 to it. So what are we solving for? We want to know the pressure when the temperature is at 298. Now, we are at a lower temperature, so we'd expect the pressure to be lower. Remember our graph. Vapor pressure, like you would expect, drops as you lower the temperature. Okay, so that's our expectation. Here's the formula. Let's start plugging in. You don't have to put anything in here yet because we have a lot of work to do on the right-hand side. So rather than carry around numbers, I'm just going to leave it ln P2 over P1. Okay? Ultimately, we're going to have to get rid of this ln and just solve for P2. But we're a long way away from that. So first thing I do, I take my vapor pressure, very important, that's given to you up here. Excuse me, my delta H of vaporization. Look, this is in kilojoules per mole. Got to be in joules per mole. Make sure you will get it wrong if you forget to multiply this by 1,000 to get it to joules. So look what I did. It's the same value, 3.31.4, but I added times 10 to the third. What's 10 to the third? 1,000. There are 1,000 joules in a kilojoule. So that's important. The denominator over Kelvin. All right, division is the same thing as multiplication by the reciprocal. So that turns out to be Kelvin. So this thing over here has the units of temperature. So if you do all that work, you get 3,779 Kelvin. Okay, what's here? T1 minus T2. I know it looks weird, but that's the way the formula works, right? Because we already moved this from negative to positive. Okay, so 334.7 is our T1. And our T2 was 25 degrees or 298. That goes down here. Okay, so take the reciprocal of this, you get this number. These are all in Kelvin, right? So that makes them 1 over Kelvin, right? So this is, put in your calculator, 1 divided by 334.7 gives you 2.988 times 10 to the minus 3, Kelvin to the minus 1. This one, flip it over, 3.356 times 10 to the minus third Kelvin. Subtract this from this. The second number is bigger than less, right? Kelvin cancels with negative Kelvin to the -1. And the whole thing, all that big number is a big number times a small number, gives you just negative 1.39. So the log of P2 over P1 is negative 1.39. So how are we going to resolve this? Well, the way to resolve this is you need the anti-natural log, which is called e to the x. And how do you get it? You hit shift or second function, which is shift ln, and it'll give you e raised to that number. And don't forget to put your negative sign in, and you use this little guy over here, which so everybody's calculator has some place to change the sign. So I'm going to go shift, well, first turn it on, right? So I'm going to go shift ln, so it gives me the e, then I'm going to go negative, okay? Some people would just call this the anti-log of 1.39. Basically, to get rid of this, I take the anti-log of this side, and then over here, I get e raised to that number. Okay, so you might have to do a little bit of review on how to do that. So e raised to that number gives me 0.249, and that is the ratio. So basically you're done, right? Because you've just figured out that, hey, what's 0.249? Well, basically that's 25%, right? Or a quarter of the original value. Well, that makes sense. At 25 degrees, the vapor pressure should be a quarter of what it is at the boiling point, because at boiling point is 60. So it goes up really quickly. So at 25 degrees, it's only a quarter of what it was before. Oh. All right, so I just lost my screen. I don't know if you guys saw that, but we're back. Okay, we're almost done. Okay, so that to me, all I really need to know is I'm done, because I take that and I just now multiply it by my original value. But if you didn't see that, has units of torr, so your answer will come out in torr. And if you multiply them out, you'll get 189 point torr. The 3 significant digits is more than enough. Hey, if you got 190 or 192, that is close enough, okay? You put that answer, you'll get full credit, okay? It is easy to make rounding error when you're raising something to an exponent, okay? Practice this idea of how to resolve the natural log of something over something else, right? And I'll just do it for you really quickly. If I wanted to show it in one more step, what I could do over here, for those people who have trouble with this, who haven't done a lot of math, I have ln of P2 over P1, and it's equal to some number. I'd say to myself, to get rid of that, I need to take the antilog, which is the same thing as e, of the log of P2 over P1. The antilog of the log will cancel out, and I'll just get P2 over P1. But I have to do whatever I do to this side, I have to do to the other side. So if I took the antilog of this side, I have to take the antilog of that side. Guys, folks, the antilog is e. So okay. Okay, that's a perfect place to stop. We are going to pick up our second video on chapter 11 on page 11, so that's perfect. Okay, and it's going to look like this when we start. We're going to start with page 11. Okay, see you next time.